So our final style of question for entropy is calculating the temperature of feasibility. So in other words, the tipping point between a reaction becoming feasible or not feasible. Generally that's going to be calculating for delta G being 0, because above delta G being 0 it's going to be unfavourable and positive, below delta G being 0 is going to be favourable and negative. So that's another style calculation we have to do. So in question 11, you're given an equation and you've got a strange kind of start. We're going back to AS2. We're looking for bond breaking, bond making calculations, and we've been asked to work out the enthalpy change for the whole reaction here. So just like before, we're going to split up into two kind of sections: bonds broken in the reactants and bonds made in the products. They've not given us a huge amount of space to work this out, but essentially in the reactants I've got NH3. NH3 consists of 3 NH bonds, so 3 times 3, 9, 1. And also consists of a CH4, which is 4 CH bonds, so 4 times 4, 1, 3. Adding that together gets me a value of plus 2825. With bonds made, I've got HCN, I might draw it out, so it's H bonded to C bonded to N, so it's got 2 bonds in it. We've got a CH bond, which is 413, be tempting to leave that one out. CN triple bond is 887. Then we've got 3 H2s, so just 3 HH bonds, so 3 times 4, 3, 6. Added together gives me a value of minus 2608. The delta H value is going to be bonds broken minus bonds made. So bonds broken is 2825 minus bonds made is minus 2603. Sorry, I don't know why I put a minus there. So minus 2603, which comes out as being a value of plus 217 kilojoules per mole. So let me get onto the bit where we're asked to kind of calculate a temperature. So the entropy change for the reaction is plus 125. Suggest why the entropy change is positive and calculate the temperature at which delta G value is 0 from the value in C part 2. So there's two parts to this question. Why is the entropy change positive? Again, just look at our equation at the top. We've got 2 moles of gas on the left hand side, we've got 4 moles of gas on the right hand side. If you're making more gas across the reaction, you're going to increase order. So entropy increases. As you're increasing the number of moles of gas. Then we get on to our temperature calculation. And the kind of derivation we use is that delta G equals delta H minus T delta S. We're saying that delta G is 0 because that's the tipping point between being favourable or unfavourable. So if 0 equals delta H minus T delta S, we can flip that round and calculate that T equals delta H over delta S. Saying to sum in my values, I have to be careful again with units. Delta H is plus 217 from the previous part. Delta S is 125, but that is in joules per Kelvin per mole. Need to divide by 1000. So remember, with your calculator, you can kind of do that within one fraction. So 125 over 1000 on the bottom of the fraction. That will come out with a value for temperature of 1736 Kelvin, which is quite high, but is actually correct. Moving on to the last question then, about the manufacturing of hydrogen from methane. So you're given an equation where you make hydrogen from methane and steam. Given a table of data, from the data in table 4, calculate the enthalpy change for the reaction of steam with methane. Looks suspiciously like another Hess law question. So CH4 plus H2O goes to CO plus 3H2. We're going from elements up to compounds because this is formation data. We've got 3 compounds, 1 element, so obviously hydrogen doesn't get any values there. Methane, we got 1 mole, it's minus 75. H2O, we've got 1 mole, it's minus 242. Carbon monoxide, minus 111. And then as we said, hydrogen is going to be 0. So to get my cycle to work, I have to flip these left-hand arrows to go down first, then up. So it's going to be plus 75, plus 242, plus minus 111, keeping that sign the same. And that will get me a value of plus 206 kilojoules per mole. Use the data from table 4 to calculate the entropy change for the reaction of steam with methane. So we've seen that style question before. Delta S equals the entropy of the products minus the entropy of the reactants. Entropy of the products, we've got carbon monoxide, which is 198, plus hydrogen, there's 3 times 131. Minus the entropy of the reactants, so we've got CH4, which is 186, plus H2O, which is 189. I can type that into my calculator as it is. Gets me a value of plus 216 joules per Kelvin per mole. Final part, use your values of delta H and delta S to calculate the temperature above which this reaction becomes feasible. So it's a little bit more cryptic here. If they're asking you for a kind of temperature above which becomes feasible, again, it's basically that tipping point between being feasible and not feasible. In other words, delta G being 0. So we're going to use the temperature of delta G being 0 is delta H over delta S. Delta H value is 206. Delta S value is 216 over 1000. Keep the units consistent. And that should come out as being 954 Kelvin. So in other words, if we had the temperature any higher than 254 Kelvin, it would become feasible. If it's lower than 954 Kelvin, it's going to be not feasible.